Horizontal separators are usually more efficient at handling large volumes of gas. This is because in the gravity settling section of the vessel, the liquid droplets fall perpendicular to the direction of gas flow, and thus are more easily settled out of the continuous gas phase. Also, since the gas-oil interface surface area is larger in a horizontal separator than a vertical separator of the same capacity, it is easier for the gas bubbles, which come out of solution as the liquid approaches equilibrium, to reach the vapor space. So, strictly speaking, from a gas-liquid separation standpoint, horizontal separators would be preferred. However, they do have several drawbacks, which could lead to a preference for vertical separators in certain situations.
Horizontal separators are not as efficient as vertical separators in the handling of produced solids. The liquid dump of a vertical separator can be placed at the center of the bottom head, so that solids will not build up in the separator. Or a drain could be placed at this location, so that the sand and clay could be removed periodically, while clean liquid leaves the vessel at a slightly higher elevation. In a horizontal vessel, it is necessary to place several drains along the length of the vessel, spaced at very close intervals.
Horizontal vessels also require more plane area than a vertical vessel with the same capacity. While this may not be of importance at a land location, it could be very important on offshore production platforms where space is at a premium. On the other hand, horizontal vessels may fit more easily in cramped lower decks and underneath heliports. Additionally, horizontal vessels have less liquid surge capacity. That is, they handle large slugs of liquid less efficiently than vertical separators. The geometry of a horizontal vessel requires any high liquid level shutdown device to be located close to the normal operating level. In a vertical separator, the shutdown could be placed much higher, allowing the level controller and dump valve more time to react to the surge.
It should be pointed out that vertical vessels also have some drawbacks, which are not process-related, but which must be considered in making a selection. For example, the relief valve and some of the controls may be difficult to service without special ladders and access platforms. In general, horizontal vessels are the most economical for normal oil-gas separation, particularly where there may be problems with emulsions, foam, or high gas-oil ratios. Vertical vessels work most effectively in either low gas-oil ratio applications or in very high gas-oil ratio applications, such as compressor scrubbers, where only fluid mists are being removed from the gas.
With this understanding of the general types of separators, let us look a little more closely at the common internal and external components of these separators. First, we shall consider inlet diverters. There are many types of inlet diverters. The first type is a deflector baffle. This can be a spherical dish, flat plate, or just about any shape that will cause a rapid change in the direction and velocity of the fluids, and thus disengage the gas and liquid.
A cyclone inlet uses centrifugal force rather than mechanical agitation to disengage the oil and gas.
In long horizontal vessels, it is sometimes necessary to install wave breakers. These are nothing more than vertical baffles spanning the gas-liquid interface perpendicular to the flow direction, which prevent waves caused by liquid surges.
Another internal separator component is a defoaming element. Foam at the gas-oil interface may occur when gas bubbles are liberated from certain oils. The foam is made to pass through a series of inclined parallel plates or tubes, which force the coalescence of the foam bubbles. Mechanical defoaming such as this may be preferable to chemical defoamers, especially as such chemical additives complicate refining.
Since a vortex could suck some gas out of the vapor space and re-entrain it in the liquid outlet, it is normally a good idea to include in a separator design a simple vortex breaker to keep a vortex from developing when the liquid control valve is open.
Another internal component is the mist eliminator. Almost every separator has one. Three of the most common mist elimination devices are wire mesh pads, vanes, and arch plates.
Wire mesh pads are made of finely woven mats of stainless steel wire wrapped into a tightly packed cylinder. The liquid droplets impinge on the matted wires and coalesce. The effectiveness of wire mesh depends largely on whether or not the gas is traveling at the proper velocity. If the velocity is too high, the liquids knocked out will be re-entrained. If the velocity is too low, the vapor will just drift through the mesh element without the droplets impinging and coalescing.
Vane-type mist eliminators force the gas flow to become laminar between corrugated parallel plates. Droplets impinge on the plate surfaces, where they coalesce and fall to the liquid collection section of the vessel.
Arch plates are designed to function essentially in the same method as the vanes. The plates are formed as concentric cylinders on which the gas impinges and coalesces.
The most common method of controlling pressure in a separator is with a pressure controller and a back pressure control valve. The valve shown here is a very common motor valve. The valve orifice is adjusted larger by moving the valve stem upward, moving the plug off the valve seat, and creating a larger area for flow. The pneumatic activator diaphragm is supplied with compressed air or gas, which overcomes the spring resistance and moves the stem upward or downward. The pressure controller senses the pressure in the vapor space of the pressure vessel or tank and regulates the control valve. By regulating the amount of gas leaving the vapor space, the desired pressure in the vessel can be maintained.
It is also necessary to control the gas-liquid interface or the oil-water interface in the separator. This is done by means of a level controller and liquid dump valve. The most common form of level controller is a simple float, although electronic sensing devices can also be used. If the level begins to rise, the controller signals the liquid dump valve to open and allow liquid to leave the vessel. If the level in the vessel begins to fall, the controller signals the liquid dump valve to close and decrease the flow of liquid from the vessel.
If these valves fail to work properly and the pressure begins to build up in the separator, relief mechanisms are relied upon to avoid rupture of the vessel.
Pressure relief valves and rupture discs are used to provide an emergency vent should some malfunction cause the vessel pressure to rise to a dangerous level. Pressure relief valves are set to open at a pressure above the normal operating pressure. Rupture discs are metal discs designed to split open when a certain pressure is achieved. These discs must be replaced when ruptured, while relief valves can open and close repeatedly.
Pressure relief devices, pressure and level controllers, and the various other internal elements discussed earlier are found on all types of separators and in some other types of processing facility equipment.